I'm Alaina.
And I'm Nathaniel, and this is Rotato.
And today we're going to show you a video walkthrough of our first robot.
Welcome to...
Alright, we're going to start this video by looking at the CAD, so let's jump right in. Alright, on screen now you can see our drivetrain that we designed in CAD for this year. So we've been experimenting the last couple of years on the team with designing just a what we call a minimal viable robot. Isn't too complex so we don't get bogged down in the details, but making it as simple as we can while still completing the goals that we set at the beginning of the season for that robot. So for this drivetrain, we experimented with using the exact same drivetrain that we did from the last year, since we had to fit within a constrained gap between the barrier and the wall. And this year we wanted to have a small drivetrain to be able to easily maneuver between all the poles on the field. And so we experimented with using just that exact same drivetrain. We did make a few changes to this drivetrain as opposed to our last drivetrain, but for the most part it's the same kind of design. So we started off by deciding on we wanted to use a Mecanum drivetrain. It was a pretty obvious choice because of the maneuverability that was needed for the game this year. And so we decided to use a 12.5 by 12.5 inch drivetrain because that would allow, even at a 45-degree angle, to be able to go between all the poles. So when turning, we'd still be able to fit, as opposed to an 18-inch drivetrain, we would not be able to turn between poles. So that's why we decided to go with a 12.5 by 12.5 inch drivetrain. You can see on the back, we put the rev hub in the back here, so that all the wires for the motors of the wheels can be going directly to this rev hub right there. We use 4 20-to-1 motors attached to sprockets and chains going to the motors, so we can have all the motors kind of central in the middle of the robot, and then chains going out to the Mecanum wheels on the side. We use a extrusion kind of structure to connect the two drivetrain sides, which allows for easily sliding on different systems when we would need them later on in the season, because the X-Rail allows us to slide in and out super easily and then fine-tune kind of the placement of all those different systems later on. Alright, let's head back over to us in the garage and see the actual physical robot. So we use Mecanum wheels, like I said before. The motors are in the middle, chains going to the Mecanum wheels pretty simply. We have all the wires kind of concealed here. We have a plate that would go over all the wires eventually. That's not on right now. The expansion hub is right here, so that all the wires for the drivetrain are concealed inside the bottom part of the drivetrain, and then all the other wires are on top.
Our next feature of our robot is our turntable. This is a turntable that we got off on Amazon. It is powered by a core hex motor. This is unique. We have our cords running through the middle of it, so that we're able to turn it 180 degrees. Next we have our lift. These are 3 continuous sliders. They are all 10-inch from Mizumi. They are connected together and they lift up the arm, the grabber of our robot.
And we use 20-to-1 motors, one on each side, with a spool, so whenever they spin, then it just lifts the lift up just like that.
Right, and on screen now you can see the CAD version of our lift. So you can see a couple differences between the actual physical version that we made and the CAD version. One being this motor placement. So after a design review that we had with a professional, he noted that the motor placement, having them at the very top, was not great for our center of gravity. It's better to have the heavy components down towards the bottom instead of at the top. We thought it would be easier so that the string could easily go up and down very easily between all the slides, but having them on the base at the bottom would definitely help with the center of gravity, because having them on the top, we would just tip over very easily. You can also see that our team decided to use 10-inch slides as opposed to the 12 or 14-inch Mizumi slides that we'd used in previous years. We decided to go with 10-inch because with the elevated height from the turntable, we only had about 12 inches at max on top of that, so we need to use the 10-inch slides to have that extra space on top. Now, one problem we did face with having the 10-inch slides is with only 3 slides, we can only reach about 30 inches. And of course the high poles, the high junctions are 33 inches. So then we do need to have this extra arm on the end to be able to reach that extra just 3 inches to be able to get high enough to actually score on that pole. Again, this is a minimal viable robot, so not everything was perfect when designing it the first time, but just trying to get a fast design out there so that we can build it and then iterate on that later on.
Alright, the next feature we're going to talk about is our grabber and holder. So our grabber is a pretty unique thing that we came up with at the beginning of the season when brainstorming. So basically we've just got a 3D printed kind of mold of a cone, and that's attached to the servo by a string, so that when the servo goes this way, then it's open, and then it's kind of spring-loaded with this elastic piece to be closed whenever it's not being opened by the servo. So we can kind of just go down on top of a cone, and then it has it already without having to close the grabber at all. That's one of the advantages of the system. And then we lift up to be able to get on top of the pole, and then the servo opens up to release the cone.
Right, and on screen again you can see the CAD version of our model. You can see a couple differences between the CAD model and the real-life version. Main one being this servo placement. So again, through a design review that we had early on after designing the robot, the CAD robot rather, we saw that having the servo on the very end of the arm would just add weight when lifting it. So we actually moved it to the back of the arm, then all the way up here, then with a string going to a arm on the grabber. That would move more mass to the rotating part of the arm instead of the far end, which would make it easier to lift. Now we made a couple of iterations of this grabber that you're seeing. We 3D printed the final version and lots of different iterations along the way, but we experimented with the different hinge sizes. Originally it was too small, and then the different hinge we would use in the middle. Then also we wanted to add a color sensor to be able to sense when the cone has entered the grabber. So that's another thing that we added in later iterations of the robot. Then also experimenting with putting holders on the bottom to hold a rubber band to be able to clamp it shut. But ultimately we decided just to super glue a kind of elastic strap going around. We also used some very grippy material on the inside of the cone here, so that when the grabber goes over the cone, it easily grabs it without any problems, and there's lots of grip there so that we can kind of wobble it around without any problems. Alright, that's going to do it for today's video. Hopefully you were able to learn a little bit about our robot design. And if you enjoyed this video, please be sure to give it a like and subscribe to our channel. Thanks for watching. Bye!